So yes, hi, welcome everybody in person, also welcome to the people online. So yeah, welcome to this Quantum at Sun webinar. So today, I'm very happy to introduce Dr. Tzula Propp, who's currently a postdoc at the Delft University of Technology in the Netherlands. And they'll be giving a talk on decoherence, limiting the cost to simulate an anharmonic oscillator. So before I begin, let me just read out your bio very quickly. So Tzula Propp studied physics and philosophy initially at the College of Worcester, Ohio, I think, and did their PhD in physics at the University of Oregon in the US, and subsequently joined the University of New Mexico Center for Quantum Information and Control as a National Science Foundation postdoc. And there they studied decoherence and open quantum systems. And I think my understanding is that what you present here was partly done in New Mexico. And so currently, so as of August 2023, Tzula joined QTech as a postdoc in the Wigner group, if that's how you pronounce it. And so researching novel quantum computation and communication applications of quantum internet with an eye towards positive social benefit. And in addition to research activities, Tzula is actively working to promote resiliency and retention of marginalized researchers in quantum through outreach programs and community organizing and mentorship, recently resulting in their co-founding of the global organization Diversity in Quantum. Yeah. So without any further ado, yeah, let me hand over to Tzula. So yeah, thank you in advance, and yeah, thanks.
Yeah. Oh, thank you so much. It's so good to be here, Graham. One quick note: my name is Tzula, not Tzula. It's a
really?
Yeah, I know. It's probably known it for 4 years, but it's always I never hear you introduce me. Yeah, indeed. It's
okay, right. I actually had a problem for about 30 years.
Yeah, it's fine. It's one letter in Hebrew that's Saudi. Anyway, thank you so much for having me. It is such a delight to be here. I've heard a lot about you through Graham. I met Graham 4 years ago when we were both stranded at the 2020 APS March meeting in Denver. And we sat down and brought coffee and lunch. Yeah, I know. And
I was at the one in Minneapolis last week.
Yes, indeed. I know. It hit me. My God, I've known Graham 4 years. Our conversation turned into a conversation about pseudo-modes and the input-output formalism, and eventually turned into a paper I wrote up about describing spontaneous radiative coupling in the input-output formalism. And so, in addition to a very productive research relationship, we've been good friends ever since. So it's a real delight to be here with you, meeting his community. So yeah, I'm here today to talk about research I did in my last postdoc as a NSF FRHTP fellow at the University of New Mexico Center for Quantum Information and Control. But it's research I'm continuing in that 20% of my time as a postdoc here at QTech, where I get to do whatever I want and not help build a quantum internet, which is also good. Yes. So as you all are aware, open quantum systems are different than closed quantum systems. Here I've got a depiction of, a ball of ones and zeros, some sort of quantum information's encoded there, right? But because light leaks out, things get blurry. A quantum system, also on the flip side, right? The light being emitted out, the information being leaked out is also how we detect and measure such systems. And this interrelationship between open systems and measurement is something that I'll return throughout the talk. So when I normally give this talk, I start by talking about life in the NISQ era, right? We're in the era of noisy intermediate scale quantum devices. And these devices do things like, Google Group does random circuit sampling. Okay, intrinsically useless, but computationally hard. And John Wei Pan's group does boson sampling, again, useless, but hard in a computational sense. And then I talk about how noise messes this up. And indeed, sort of the three main points of my talk I normally emphasize are that when you introduce noise into devices like this, but also into more simple toy models, your quantum dynamics or your quantum information turns classical. And that makes it easier to simulate. And furthermore, a shocker, right, to a lot of people, is that this happens more quickly for more macroscopic systems. But since this is a community of open systems people, I don't think you're going to be shocked by any of these results. And you're not like industry funders who are really gung-ho about selling quantum devices, who I have to de-hype and be like, no, they're not going to be as good as you think, because noise exists. So in addition to these 3 points, which are 3 of the main takeaways from my talk, I have 2 additional ones specifically for you all, which is that fourth, showing points 1 through 3 doesn't just require understanding the quantum dynamics of the system, but also requires understanding the measurements of that system. Which measurements are going to be interesting? Which measurements are going to be sensitive to quantum features? And to make it a little easier on my neck, I'm putting you on top of my quantum noise book. Here. Good. And that noise interacts with quantum dynamics in a way that is that leaves a signature in the measurement record. That's sort of one of the things in this paper that I recently published that I think is new and has not really been in the literature before, in addition to quantifying those 3 points. Okay, so let's dive in. So what happens if we put fancy schmancy quantum devices in baths? What if we give them thermal couplings to a thermal environment, or even a 0 temperature environment, so just energy can leak out? What is the computational complexity in the presence of noise? Well, there's sort of 3 answers you could give. One is, I've taken undergraduate quantum mechanics. I know decoherence takes superpositions to mixtures. Mixtures are easier. You just flip coins. You don't have to deal with qubits, so it's got to make it easier. A second answer you could give is, sure, well, maybe the quantum dynamics get drowned out by classical noise, but there's just a polynomial overhead. It's the same system, just noisier. And yeah, you might have to take more data, but it's not really fundamentally a harder problem. Just a problem with a constant prefactor in difficulty. Or you could give an answer I really disagree with, which is that the dimension of the density matrix is larger than the dimension of the state vector. So open systems are always harder, and noise has to make it harder. I disagree with that, as I said. But we're going to sort of dive in and quantifiably answer this question, not for Google's Sycamore processor or for Jean-Wei Pan's boson sampler, but for a nice, easy toy model. Easy, doable toy model. And the landscape we're going to do this in is phase space. So this is a project that Ivan, Tamim, and Shioni, who was then a postdoc at SAQuTI, all started together. And then they were sort of stuck for reasons I'll come back to. And then I was able to unstick them. And then I was finishing up my time. So John DeBroda, my favorite cubist, helped me out at the end of it as well. So phase space is a natural space to study the quantum to classical transition. Why? Well, for one, you can put quantum and classical states on the same plot. And there's not a lot of formalisms of quantum mechanics where you can do that. Also, there's these nice features that appear. For instance, if you plot a Wigner function, right? You have these interference fringes when you look at the marginals that say, hey, there's quantum stuff happening. These come from negative quasi-probability distribution and subPlanckian structure, giving rise to measurement record features that you can detect and say, this momentum never happens for this cat state. And for those of you who don't know, a cat state is a superposition of 2 different coherent states, usually with opposite amplitude. Another good reason to study decoherence in phase space is that it's really well studied already. Wojciech Zurek has a wonderful amount of literature on this, especially pioneering the work from the 80s and 90s and into the current day too, showing how, yeah, sure, in the top, you've got this quantum nonlinear system with all this subPlanckian structure and all of this negativity. And then you turn on decoherence, and what do you get? You get a Lorentz attractor and not much negativity at all. And things look pretty classical. Good. So that is sort of the landscape in which we're going to study decoherence in this paper. And the system we're going to study is actually a very old system. It is the nonlinear optical Kerr effect, which was discovered in 1875 by John Kerr, Scottish physicist, who was so old that, you know, his papers sound like, the thought which led me to the following inquiry was briefly this, that if a transparent optically isotropic insulator, yada, yada, yada. It's not how we write papers anymore. The gist of it is if you take a piece of glass or something like a piece of glass, shine a really intense laser on it, you can make the light coming through perpendicularly experience a amplitude dependent index of refraction. That's how I think about the classical Kerr effect. It's like an index of refraction with frequency, except now we have it for amplitude as well. It's a chi3 interaction, yada, yada. For a quantum optician, the Kerr effect is a quantum phenomena. Well, the quantum Kerr effect is a quantum phenomena, and it's this Hamiltonian describing bosons. And notably, this is the simplest possible nonlinearity you could add to a simple harmonic oscillator. So it's a natural thing to study. It's also useful for making qubits out of bosons because a harmonic oscillator has equal energy levels, and that's not very good if you want to isolate just two of them. So adding a nonlinearity is very nice. But for the purpose of this talk, the important part about the Kerr interaction is that it's a structure generating process, taking an initial coherent state through a rather dramatic array of very quantum states. These high order superposition states, I call them kitten states. So right now, that would be a 4 kitten state. And you see it go now to a 3 kitten state. And even, wait for it, through the 5, it all swirls right there. That's the cat state we talked about in the last slide. So this phenomena takes this, the most classical possible quantum state, the coherent state, into this quintessentially quantum cat state. And along the way, it has subPlanckian structure, it's got negativity, it's got a lot of the things you'd want to see. And so now we ask the same sort of question. What happens when we put this in a bath? And eventually it recoheres back to an initial coherent state. So you'll see right there. That's where it resets. So on the right, we've got the closed system. And on the left, we've got the open system. And initially, they do pretty similar things. But whereas the right starts to pretty quickly form these discrete superpositions of coherent states, these kitten states, the open system just swirls around and doesn't do all that much. And again, we've got all this fine structure, all this negativity on the right. On the left, it looks blue, but that's just because it's taking the lowest value to be blue. So it's really just 0. Not much is happening. And indeed, once those final swirls in the middle disappear on the left, the donut contracts in width a little bit as you go from a superposition, slightly a superposition, to a genuine mixture. So this is just a video. This is just a numerical simulation that I wrote up about what does the Kerr interaction actually do to a coherent state when you add noise. But this isn't really predictive. Again, this is just a video. How do we predict the behavior and understand it? Because, you know, we're theorists, not necessarily just computationalists. So there's a lot of value in that too, because computation is hard. So being the sort of theorist I am, I solved this problem in 3 different ways. The first 2 are things I developed, and the last one is what the numerics, not in this video, but in the plots I'm going to show later in the talk, are based out of. This numerics in this video don't work for large alpha. I just sort of brute forced it in an interesting way. Okay, so the first way to solve this is just for the closed system, and it's using an idea from Bielnicka Barula in her 1968 paper about generalized coherent states. If you have a unitary operator that has certain properties, which I can go into after the talk if you're interested in, you can perform a discrete Fourier transform and decompose the state at any time t sub q, where q here is a rational number, into a discrete superposition of coherent states, all with different amplitudes. And that's great. It gives us the time at which these kitten states form. Good. As well as some idea about the symmetries underlying them, which I'll come back to. And then there's this I sometimes call it the nightmare formalism. Just what I came up with when I've tried to brute force solve this problem in the Fock representation. It turns out, though, that it's doable, even in the open system, because each diagonal stripe of the density matrix is completely self-contained. And even if it's kind of a nightmare, if you only care about one stripe at a time, things are kind of manageable. And it allows you to prove some nice properties, as well as make these nice videos. But it doesn't scale. It scales pretty badly. And then we have the main workhorse of this work, which is Fokker-Planck equations for phase space evolution. This is based on the pioneering work by Stubinska and Milburn and Wojciechowicz, studying the Kerr effect and deriving how to actually model it in phase space. So this is the one we're going to talk about right now. So what is a Wigner function anyway? Well, it's a way to turn the density matrix, rho, into a function of coherent state amplitude, alpha. Here, T of alpha is the Fourier transform of the displacement operator, and it's the closest thing you can get to a delta function, given that x and p don't commute. So what can you do? And below this, I've written the master equation. This is the equation that describes open system evolution in terms of Hamiltonians and jump operators. And what we can do is turn these two into something called a Moyle bracket, plus the open system terms. So when you just plug this all in and do a lot of math, what you find is an equation of motion for the Wigner function. It looks like this. It's not so crazy, actually. What do you have? Well, you've got a mean field rotation. Things rotate. You would expect that. They do that in the simple harmonic case too. Just here, they're doing it in a slightly different way. You've got a Gaussian shear. That's sort of that at early times, you had like a banana-ifying effect. And this third term, the non-Gaussian evolution, is what's giving rise to fine-grained structure and the sort of quantum features and negativity we care about. So, I should have said this, we consider here single photon loss. That's what I wrote as the jump operator. But in general, you could consider photons coming in too, and then you'd have some thermal terms. We're going to set n thermal to 0 here. So these are the open system effects. You've got drift, things go down towards the origin, and diffusion, things spread out. What's nice about the phase space representation of open quantum systems is you actually do separate out decay, which is drift, and decoherence, diffusion. I don't really know of any other formalism that does that. Yeah, that was something that really impressed me when I got involved in this work. But the real reason to use this formalism is the truncated Wigner approximation, which is this great thing where you say, hey, forget the Moyle bracket and all that crazy star algebra. Let's just pretend it's a classical Poisson bracket, and you get rid of this non-Gaussian evolution, but you have the rest. And this is what's the word? This is a tool that always you can do, right? It's not like just throw away this term. This is like a rigorous method to separate out the quantum from the classical in your Fokker-Planck equations. And what you end up with is a system of equations describing something that stays positive always. And here, the truncated Wigner approximation here for the closed system just kind of spaghettifies and spirals around. And that's what you'd expect. If for the simple harmonic oscillator, you have a ball that rotates all around at the same frequency, right? Here, different amplitudes are rotating at different frequencies, so they spaghettify. And crucially, because this is a positive map, it permits semi-classical sampling. Okay, good. So this is how we're going to study the state evolution in phase space. So let's look at some numerics. Well, on the left in each of these boxes, we have the exact quantum dynamics. And on the right, we have the truncated Wigner approximation. And they don't really look very similar. This is for alpha naught equals 6, which is already well past what I could do with that little diagonal stripe video method. That's why it looks so nicely high resolution. So these look nothing alike. However, if I introduce a little bit of decoherence, a little bit of coupling to the environment, pretty quickly they start to look more similar. Yeah, in the first one, you can kind of see the spiral. In the second one, you can see this donut, but there's still some interference at the center. But by the time you get to 5 pi over 3 kappa, this time where the 6 kitten state forms for the second time, they look pretty indistinguishable. And if I increase decoherence even more, even at earlier times, they look pretty indistinguishable. So check, right? We did it. We showed that quantum stuff becomes classical when you introduce decoherence, but not so fast. What we're interested is something quantitative, and in particular testing a hypothesis that even a little bit of decoherence decreases the simulation cost for some hard measurement. So that poses the question, which measurement? So now I have quiz time for you all. Which measurement operators are sensitive to complex, to complex not in the math sense, but like complicated. Which measurement operators are sensitive to complicated fine-grained phase space structures of states, and specifically Wigner functions? Does anyone in the audience want to say? I can do the Jeopardy song if you want, while I wait.
Projection. I'm just going to guess projection. That's the only emergence I think of.
It's not. Okay, technically it is a projective operator, but that's too vague. Which measurement operators? There's tons of projective operators. Which ones do you think are going to have to do with phase space?
Oh, okay. So you mean in terms of like a dagger rather than type of measurement?
Yeah, not quite. Think a little bit at an angle to that. What can you build out of A and A dagger?
Quadrature.
Like quadratures. Exactly. It's field quadrature.
Okay.
It's X and P, and specifically, thank you for doing that with me. I appreciate it. Specifically, it's symmetrically ordered combinations of X and P, but to different powers. Also, you can also think about these as contributing to an X sub theta, which you could then expand out into like cosine of X plus cosine theta X plus sine theta P, and then raising that to some power. X sub theta is the moments along a particular angle. And the thing about the Wigner function is that it gives the right marginal distributions when you integrate out over the perpendicular direction. So if I draw that line along theta, and I integrate it along the perpendicular direction, I get a distribution. And that distribution has a lot of features that are kind of going away with decoherence. And that distribution is uniquely defined by X sub thetas and all the expectation of value of X sub theta to the n for all values of n. Except in very pathological cases that don't come up in quantum mechanics, functions are described by their moments. Good. There's a math fact for you. So this is our goal. We want to study the XP symmetrically ordered operators that are like X sub theta to the n or X to the n P to the m. But we have to understand which ones are going to be interesting. And not only that, but why are they going to be interesting? Because it's physics. We want to understand what's really going on. Oh no, I'm going to call my computer's bluff. It says it's going to restart in 5 minutes. I don't think it's going to restart in 5 minutes with a mandatory update. Anyway, so which ones, why, and when? If we take this cat state and we look at its X marginal, there's nothing quantum. You just have these two bumps and you can't tell the superposition from a mixture. It's only by looking at the P marginal that you see these interference fringes. And you say, something quantum's happening. So, given that the cat state is one of the states formed in this, we know that not all of these moments are going to be interesting all the time. So how do we understand which ones are interesting when? Well, we have to do some math. And that involves studying the normally ordered moments, the normally ordered operators of A dagger and A, the creation and annihilation operator, going from that to the symmetrically ordered ones of A and A dagger, and then only then going to the ones of x and p. Just a quick review, because some of you may not have seen operator ordering before. This is just some foundational quantum optics that everyone should know. So if you don't know it, now you're getting to know it. Normal ordering means you put the A daggers on the left, the A's on the right. So the number operator is normally ordered by itself. And there's an associated quasi-distribution function, the P function for this one, which doesn't always exist. But yeah, anyway, this is just important to know. There's certain functions associated with the operator orderings. Anti-normal operator ordering, you stick all the A's on the left, A daggers on the right, and you have to do some commutators to get there. And for symmetric, you make sure there's an equal number of going one way and the other way. On board? Yeah, good. No questions. Okay, good. So for the normally ordered operators, you can actually calculate them in the Heisenberg picture, again, for the closed system. And with that, you can calculate an expectation value of A dagger to the nu, A to the mu. No problem. And what this reveals is actually the sensitivity to the kitten structure, and in particular via the cyclic group Zn. So if you just say, what is the expectation value of A dagger to the nu, A to the mu with an arbitrary n kitten state, you find that a lot of the time it's 0, unless the difference in nu and mu is an integer multiple of the number of kittens. You don't get anything, or you don't get anything interesting up to exponential suppression. Why is this? Well, imagine I have this kitten state, right? And in principle, each of them have an individual e to the I phi I, an individual phase. But let's imagine they're all equal for now. What happens when I apply the annihilation operator? Well, each of those phases get rotated by e to the I 2 pi I over n. So they go from all being at 0 to uniformly distributed around the circle, but at 6 locations. I apply the annihilation operator a second time. The same thing happens. They move over, and now they've sort of gone to 3 points. And we do it again. Still, they're equally distributed in such a way that they will average out to 0. And we do it again, and we do it again. And only when I've applied the annihilation operator an equal number of times to the number of elements in the superposition do they recohere back at the same value. So that gives rise to this phenomena we saw before. And is also indicative sort of the element of symmetry here, which we're going to come back to. In particular, well, what I should say is that particularly this means that only when there's a match between the symmetry of your operator, here it's going to be the difference in nu and mu, and the symmetry of the state n, do you get something interesting. So now, but that was for the normally ordered ones. How do we know it's the same for the symmetrically ordered ones? Well, we use this diagonal stripe formalism, and you can sort of prove 3 things from this. It's in the paper that for anharmonic open quantum systems that are number preserving, the recurrence times of operators depend only on this difference, mu minus nu, not mu and nu separately. These are recurrence times are unchanged by operator ordering because that preserves the difference mu minus nu. When you do a commutator, you remove a power of A and A dagger together, so that difference stays the same. And thirdly, that Markovian open system effects do not change the recurrence times because the correlation function depends on the same, defer 8 hours for this update. Ha, I knew it wasn't going to go. Pretty much, you can decrease or increase relative contributions in terms of frequencies to a signal, and you're not going to change the periodicity of the signal. You're just not. You might change what it looks like, but you're not going to change its periodicity. Great. So that's in the paper if you want to look at that. And what this comes down to is a period or a recurrence time, t sub mu minus nu. And here the S is saying in terms of all operator orderings. And then to get that to the x and p, or x sub theta to the n plus m, You just do a binomial expansion, and it's not too bad. And indeed, that's what we do. So if, for instance, you have x squared p to the fourth, and you want to ask how many recurrences are there, well, the combined power is 6, and that means that the difference in nu minus mu can go between 0 and 6 in steps of 2, and then you can predict them all. In fact, it has to do with Euler's totient summary function, which was really fun to figure out. Probably totally irrelevant, but if you really like it, it's a footnote 6 in the paper, that you can actually predict how many recurrences are going to happen. But more importantly, we can figure out when these recurrences are going to happen based on the symmetry of an operator. So here, let me go back. In that last figure, this was the actual expectation value. I went to it fast, right? So it's going between 0 and some positive value up and down. And then in dashed line, I have the truncated Wigner approximation. But why don't we just look at the difference between the quantum expectation value and the truncated Wigner approximation? Good. That's what we're doing here for a couple different choices of theta. And for the rest of the talk, we're really going to focus on x sub theta, because that's the more meaningful thing to discuss. What we see is that indeed, yeah, at small times, there's a deviation from the truncated Wigner approximation, but that's just a quantum artifact, actually. That disappears for a large initial coherent state, as you'll see very shortly. There are times when the quantum state in the second and fourth cutout is doing something really interesting in quantum, but the symmetry of the operator does not allow you to probe that. And it's only at this third time, where you have the 6 kitten state, that you actually see something happening in the measurement record. Good. This was very surprising to some people when we showed it. They thought because quantum stuff was happening, it should show up in the measurement all the time. Not how it works. You have to connect the right measurement to the right quantum phenomenon. Okay, good. So now what we can do is sort of average over the angle theta, normalize by the coherent state magnitude to the power n. And this way we can compare across different values of n and alpha naught. And what we see is indeed, when we go to a larger coherent state, that initial deviation goes away or decreases. And also the effective decoherence is more dramatic. If you compare the lines on the left to on the right, you'll notice that they are much more clustered around the bottom. The quantum oscillations on top of the truncated Wigner approximation are being suppressed. Good. Good. Maybe not too shocking. Now, what we can do is we can remember that all these simulations are done on a numerical grid with a grid size delta r. And if we find a suitably small grid size dr, we can consider that to be the true value and ask, how much do we mess this up when we go to a larger value? And sure enough, as you increase decoherence, which prevents the formation of this complex structure, you decrease the error induced by using a finite grid. Decoherence suppresses errors induced by a larger numerical discretization that should be delta r. It's sort of like a TV, right? If you want to watch, God, what's a new movie? I don't go to the movies. The new Hobbit movie. You're gonna need a fancy Panasonic HD TV to do it, right? But if you want to watch your your parents or grandparents like little VHS tapes of home videos, you can do it on the old dial-controlled Samsung P3202 in the attic. Why? Because there wasn't that resolution to begin with. Yeah, good. And interestingly for me, or perhaps most compellingly for me, is that this effect, this suppression of the errors induced by discretization becomes, with decoherence, becomes much more substantial for a more macroscopic initial state. Notably, if you look on the plot on the left, there's 3 orders of magnitude difference between the bottom and the top line at maximum. On the right plot, it's 5. And we're only going from alpha naught equals 3 to alpha naught equals 6. So the simulation's becoming easier, faster with decoherence. Good. So the story so far. For measurements which are sensitive to the quantum structures of states, decoherence erases their fine structure, which decreases computational cost and suppresses quantum behavior. And in order to show this, I had to tell this story relating the states and the measurements to their shared symmetry related to the algebra, the cyclic group Zn and the Weil-Heisenberg algebra. So at this point, I want to just pause and assess our progress. This is the Netherlands, by the way. This is in Amsterdam, I'm pretty sure, where I took this. It's a very pretty place, except in the winter. Then I wish I was where you were, because it's summer. So decoherence turns quantum dynamics classical. Yeah, we've seen this already. And we've quantified it too, right? In terms of those deviations from the truncated Wigner approximation. Decoherence makes computationally expensive simulation cheaper. Check. Absolutely, that was what the last plots were about. And both of these happen faster for more macroscopic systems. Also check. Hopefully you're convinced of this. I also hope that you're convinced of this fourth point, that to actually understand and quantify these things, as opposed to just showing two pictures and saying, yeah, they look pretty similar, actually required specifying a measurement. Before I was brought onto this project, they were really trying to do this with states. And turns out the Hilbert-Schmidt distance between states, it wasn't working. It really wasn't showing these two things coming together in the same way. And again, this is sort of where my background in measurement theory came in and said, well, but what's the measurement? Because that's the thing you have at the end of the day. So what I'd like to focus on for the remainder of the time, briefly though, is this fifth point, that noise interacts with quantum dynamics. And this leaves a signature in the measurement record. This is sort of one of the last points in the paper and something, I don't know, I care quite a bit about. So at this point, you want maybe someone who's taken a quantum optics class and done the actual cat problem says, objection, what about coherence? I've done this calculation for a cat state. I've figured out its expectation values of its P operator to arbitrary power. And yeah, indeed, the coherent contribution is exponentially suppressed. This looks like a decoherent resistant quantity. If I take a cat state and I turn on decoherence, its moments don't change that much. What the heck is going on here? Well, the answer is this, that sure, decoherence after a unitary doesn't change things very much. Here we have a 3-kitten state. The coherence goes away, right? But it's still a mixture, right? A highly structured mixture. But decoherence during unitary evolution prevents the formation of complex states in the first place, mixed or pure. And that's the difference. Also, for completeness, decoherence before the unitary would just make the whole thing happen smaller, right? The coherent state is an eigenstate of the annihilation operator. It just shrinks, and then it does the same thing, but smaller. So concurrent dynamics prevent the formation of complex mixed states as well. And this is due to a failure of something I call the convex noise model, which I introduced way at the beginning, right? This idea that maybe the quantum dynamics are just getting drowned out by classical noise. How can we test this? Well, first of all, again, someone should object and be like, no, what that top line says doesn't make sense because classical states don't have density matrices. Okay, so the better thing to do is write this in terms of Wigner functions and then check. Every classical state has a Wigner function. Good. Because of the linearity of quantum mechanics, every expectation value will inherit the same convex structure. And if you then define a deviation from the classical, as we just did, this function P of t comes out front. So that's our tool. That's what we're going to use. So now let's define P sub n of t to be the value of P of t. We just solved for it on the left for an order n operator, right? And this top part of the fraction is precisely what we calculated before. And this bottom part is something else we can calculate. And we calculate what is the value of P of t sub n at the time of the cat state formation. And we compare it for different values of n. And since all the even n's contribute to share the symmetry, right, of the cat state, because they all have the bilateral symmetry, They're all sensitive to the structure here. They're all doing something quantum. And indeed, these are not flat lines. The dashed lines are what we'd have if this was a convex noise model. And what we find is that higher order observables become classical faster. Intuitively, this makes sense. These are the measurement operators that are more sensitive to quantum structure, the fine-grained details, the things that get washed out faster. But indeed, a convex noise model says that's not what happens. So the measurement statistics reveal deviation from convexity is one of the sneaky results of this paper hidden in there. And the final question I'll discuss is, could we have predicted this? For the Kerr interaction, the answer is yes. You can think about the evolution, right, in terms of a super operator containing these jump operators L, as well as unitary Hamiltonian evolution. And sure, everything commutes for just one time step, but because L and H don't commute in general, when you integrate over time, you can't just pull out the super operator to the left and do all the unitary stuff first, or vice versa, right? Then you would have a convex noise model. Furthermore, it's kind of more dramatic. There's a deeper failure happening here. Not only do L and H not commute, but let me see, the commutator math works like this. H Kerr has operator rank 4, A has operator rank 1, the commutator removes 2, and then you add them together. So you get an operator of rank 3 from the commutator. Okay, good. But let's stick that in a commutator. Now we've got a commutator of rank 4, a commutator of rank 3, H Kerr rank 4, A dagger, A squared rank 3. The commutator removes 2, and then you're left with 5. Uh-oh. The Lie group is exploding. So not only do these things not commute, but they conspire to generate an infinite Lie group, and that's not something we understand very well, but we can certainly expect it to not be very well behaved. There's also another property going on here. If you assume a convex noise model, you can show that this is in one-to-one relationship. This is not in the paper. This is what I hope to do next. Well, this is what I've done and will eventually publish next, is the effect of the Lindbladian on the closed Wigner function has to be uniformly proportional to the difference between the closed and the classical dynamics across phase space in order for a convex noise model to be true. This just comes from playing with the math and the differential equations quite a bit. And this kind of suggests a connection to unital maps. When you think uniform across phase space, that's sort of maybe what should come up. And yeah, I've talked with Carl a little bit about that. In general, prediction is a work in progress, but this is sort of the hint at where I'm going next. And I just applied for professorship here. So if they hire me and I get graduate students, this is one of the ways we'll be going. Anyway, so the main takeaways. Decoherence erases fine scale structure, improving the truncated Wigner approximation and improving the computational cost of numerics, especially for more macroscopic states. To show this, we must identify what measurements will be interesting and when. And when noise interacts with quantum dynamics, it has a signature in the measurement record, and I'm working on a way to predict it. So I just want to lastly say that this has sort of been part of the decoherence and noise part of what I do, which indeed, what happened there? That top one is the paper that I just published. This bottom one is the one that came out of the conversations with Graham. And yeah, I care a lot about decoherence and noise, but also about modeling quantum devices. And if you were at APS, maybe you saw this talk by Yanis, one of my collaborators, on that. But I'd also like to just emphasize this diversity in quantum part, because as Graham mentioned, we just founded an organization, and along with Denise Ruffner, Cindy Bacon, and Mike Daskell, who's a Quantum Foundations person. So maybe you all might know him. Anyway, we're interested in learning more about supporting quantum scientists across the continents. And I know there's some expertise in that with you all. So I'd be very interested in talking about that. And we have a summit coming up where we'll have industry partners as well as speakers and things. So if you're interested, check out our Substack. Yes, good. So with that, I'd like to thank all my collaborators, Ivan, Tamim, John, and Shioni for help on this project, Carl for just a little bit of guidance, on what the heck to do with these convex noise models. My cat Ubu, who's always very helpful. And yeah, this is the Rio Grande at sunset. Thank you all. I'll take your questions.
Yes, thank you, Tzula, for that very interesting talk. Are there any questions? Okay, I can maybe start with asking a question and then wait until any of our online participants ask questions. So I had maybe a very basic question about the truncated Wigner approximation. Had a slide where you had the equation of motion, like more towards the beginning.
But ask your question, I'll get
it was more about trying to understand more about this approximation. So, more specifically, once you perform this approximation, you mentioned that you get rid of the non-Gaussian, or the terms that contribute to the non-Gaussian evolution. So these are the quantum terms, right? After you perform this approximation, does the resulting equation give you any indication about what's happened in the quantum dynamics, or is that completely gone? So the reason I'm asking, I'm trying to think, like, you could maybe represent the quantum, so you could use the truncated Wigner approximation to come up with this equation of motion to describe what's going on classically, and then you can incorporate like the quantum part as a perturbation. So in a sense, you can incorporate, in a sense, like a mean field kind of motivated quantum. So
and people
in other words, does this give you any idea about what's happening with the quantum dynamics?
So the short answer is no. If you just have the truncated Wigner approximation and you don't know where it came from, yeah, you don't have any access to what those higher derivatives look like. There's a lot of flexibility in what they can look like. Notably, it's not fair to call the truncated Wigner approximation completely classical, because it's really semi-classical. Even the truncated Wigner approximation contains the fact that the vacuum contains some uncertainty. It doesn't contract your phase space to the origin, it contracts it to the ground state. So there's still a little bit of quantum there. The uncertainty principle. Yeah. Okay. But to your question about using it as sort of a baseline and then doing perturbative analysis on top of that, yeah, I think I've read papers about that. Indeed, the truncated Wigner approximation is nice because you can do it easily and then sample it easily. And then, yeah, looking at just little quantum fluctuations on top of it. Yeah.
Okay. So, yeah, how do you, maybe this is too broad of a question, but how do you even go about solving that type of equation? Because to me, I'm not somebody that works in phase space, so like, how do you even, because it looks quite complicated.
You have brilliant computational physicists to work with, is the answer.
Okay.
Who then, actually, they don't even do it with this equation. They go to reciprocal coordinates, and then they discretize and solve things there.
Okay.
But it's hard.
Okay. Also, maybe if there's any, I can't see any questions in the Q&A, so maybe I can ask one more question. If there's...
I can also ask a question.
Yeah, sorry.
No, go ahead.
So it was more a question about, you mentioned more when you were looking at the measurements, you looked at the moments of the quadratures. So you had x to the 6, and you mentioned that, if I'm right, that you can only see the quantum effects in these higher order quadratures, right? So you need to look at least x to the 6 to see this. If I understood correctly.
No, sorry. So let me go to the right slide that will explain this perfectly, which is here. I'm just going to exit this, sorry, and I will just share my screen normally. I will go to this slide.
Yes, yeah.
You have, it's not that you need higher and higher order moments to see it.
Okay. You need the right one.
You need the right ones. It's true that if you want to be sensitive to the quantum structure of like a really, really short time kitten state, like very, very early, yeah, you're going to need it to use a really high order moment. But it's not that the one needs to be sufficiently high. It needs to have the right time. The time of recurrence of the operator needs to line up with the symmetry of the state. So yeah, there's interesting quantum dynamics happening here too, but this operator doesn't care. You would need something with x sub theta to the 9, if I counted correctly.
Yeah. And for somebody who's not an experimentalist, how feasible is it to measure? Can you measure arbitrary moments in experiment, or is there some limitation?
So I think that's a great question. How does this work? Okay. So you can it's homodyne, right? So you pick a measurement quadrature and you're measuring values of it. So what you get is actually you're not like measuring the moment, right? You're getting a distribution of outcomes. And then from that, you extract higher and higher order moments.
Okay.
Does that make sense?
Yeah, no, that makes sense. Yeah.
Okay, good.
So yes.
So, Tzula, thank you very much for the fantastic talk. I have two questions. One is, you stressed a few times the advantage for computations of adding the coherence. Huh? What does it mean in the NISQ era? So if does it have any implications for quantum computing?
Yeah.
Or are you promoting just dissipative quantum computing?
No. So, okay. That's a good question. Indeed. So the original folder title for this project, as it was handed to me, is NISQ is bullshit. Indeed, the hunch behind this whole project is you're not going to be able to do something quantum advantageous if there's noise, because noise makes things less quantum. And indeed, it does so faster for larger alpha, or for more macroscopic state. The implication is that NISQ isn't really going to work. I think a lot of people already suspected this, but yeah, I'm not against quantum computation, but especially in the US, where it's very like investor driven, they have all these terms. It's like, oh, this angel investors pumping money into the quantum sector. There's a real need to de-hype it and say quantum computing is revolutionary, but it's not going to be revolutionary with our near-term noisy quantum devices. That's going to be a low-risk, low-reward proof of principle. I'm a fan of error correction. My work with the quantum internet stuff, I want to make sure that when the quantum internet is eventually really developed, that it works, that it's accessible to everyday people, and that it's not like that it's anti-dystopian to the extent we can make it. But yeah, the implication for NISQ is that NISQ is probably kind of not going to work for precisely this reason. That the really interesting quantum problems are like the many body physics problems. That's a very macroscopic quantum state, and it's going to be very sensitive to decoherence. And sort of like this part, right, where I talk about convexity, it's not like you can just take more data. Another motivation for this project was an email exchange between Ivan Deutsch and Scott Aronson, where Scott Aronson more or less said, if there's more noise, you take more data. And Ivan was like, that doesn't make sense. The noise can change the data itself. And that's what's going on here. You're not just adding noise to the thing you want. You're changing the thing you want. You can still do zero noise extrapolation, and non-convex is not non-Markovian. I'm still sort of thinking about whether to frame it as like a stepping stone to non-Markovianity or as an orthogonal direction. But it's not crazy unmanageable, but it's not just adding noise. And indeed, if you look at Google's paper, they do a lot of work to convince the reader that the noise is of this simple form. To be fair, because they're doing random unitaries, it does average out to the simple form. But only once you average over every single unitary you could possibly do. So hopefully that answers that question.
No, thank you very much. And you answered my second question by closing the presenter mode, because I wanted to ask you whether you use Keynote or PowerPoint.
I used a little bit of these computers for some reason are forbidden from having Keynote at my new job, but I have a copy of Keynote, and I did one of the sneakiest things I've ever did, a bit of social engineering to get the administrator password for this network computer to install Keynote. I just told them I was supposed to have the password and I wasn't.
Wonderful, well done.
Graduate students, take note.
Is there any other questions, maybe from our online participants? I can't remember the chat.
Keeping a low profile.
Okay. If there's no other questions, then maybe I can just end by thanking our speaker again. So thank you, Dr. Tzula Propp, for the great talk, and